NENOMATICA, where mathematics meets YouTube excellence. Welcome! In this lesson, we will build an intuitive cheat sheet of logarithm properties. We'll move step by step with visual rule cards and quick numeric examples. Let's begin with the two most fundamental facts. First, the logarithm of 1 is 0. Second, the logarithm of the base is 1. Next, product and quotient rules. Product turns into addition. Quotient turns into subtraction, and a reciprocal flips the sign. A quick example in base 10. Log 10 of 5 equals log 10 of 10 over 2, which is 1 minus log 10 of 2. Power rules. An exponent on the argument becomes a multiplier. An exponent on the base becomes a divisor. Together, m over p appears. The root versions are just fractional exponents. Change of base and reciprocity are the power tools for switching bases. The product of log b of a and log of b equals 1. And log base b of a equals log base c of a over log base c of b. Two lovely exponential identities. First, n equals a raised to log base of n. Second, x to the log base I of y equals y to the log base of x. The problem asks, given a squared relation, a squared plus b squared equals 7ab, find the value of log of the quantity a plus b all over 3. Step 1. Start with the given condition. A squared plus b squared equals 7ab. Step 2. Replace the left side using the perfect square identity. A squared plus b squared equals the quantity a plus b squared minus 2ab. Therefore, the quantity a plus b squared minus 2ab equals 7ab. Step 3. Add 2ab to both sides. The result is the quantity a plus b squared equals 9ab. Step 4. Divide both sides by 9 and rewrite as a square. The quantity a plus b over 3, all squared, equals ab. Step 5. Apply the logarithm to both sides. If two positive expressions are equal, their logs are equal. So log of the quantity a plus b over 3 squared equals log of ab. Step 6. Use the power rule and the product rule of logarithms. The power rule says log of x to the n equals n times log x. The product rule says log of x, y equals log x plus log y. Therefore, 2 times log of the quantity a plus b over 3 equals log a plus log b. Step 7. Divide both sides by 2 to isolate the desired expression. Log of the quantity a plus b over 3 equals 1/2 times the quantity log a plus log b. This is the final result. In this lesson, we will evaluate a logarithmic expression using the Pythagorean relationship a squared plus b squared equals c squared. We'll begin by writing the problem clearly on the screen, and then transform it step by step into something we can compute directly. Step 1. Start from a squared plus b squared equals c squared, and isolate a squared by subtracting b squared from both sides. So a squared equals c squared minus b squared. Step 2. Recognize a classic pattern. C squared minus b squared is a difference of squares. That factors as c plus b times c minus b. Therefore, a squared equals quantity c plus b times quantity c minus b. Step 3. To connect to the target expression, we take logarithms of both sides twice, once with base c minus b and once with base c plus b. Step 4. Apply the power rule. The log of a squared becomes 2 times the log of... Apply the product rule on the right. The log of a product becomes the sum of the logs. Step 5. Evaluate the log of the base itself. Log base c minus b of c minus b equals 1, and log base c plus b of c plus b equals 1. That simplifies both equations nicely. Step 6. Now compare our simplified right-hand sides with the target expression. 1 plus log base c plus b of c minus b equals 2 times log base c plus b of a, and 1 plus log base c minus b of c plus b equals 2 times log base c minus b of a. Adding them together gives the value of the target expression. Finally, factor out the common factor of 2. The evaluated expression is 2 times the sum of log base c minus b of a and log base c plus b of a. Example. We will simplify a logarithmic expression using a given condition, step by step, following the exact structure shown on the screen. Problem. Given the condition xy plus yz equals 2xz, simplify the expression log of x plus c plus log of x minus 2y plus c. Step 1. Use the product rule for logarithms to combine the two logs into a single log. Step 2. Expand the product inside the logarithm and gather like terms. Step 3. Substitute the given condition, xy plus yz equals 2xz. Step 4. Recognize a perfect square, x plus z, quantity squared minus 4x, z equals x minus c quantity squared. Step 5. Use the power rule of logarithms to bring the 2 out front. Therefore, the simplified expression is 2 times log of x minus c. Great job following the steps exactly. In this example, we will extract a clean algebraic structure from a sentence and then prove the final statement step by step. First, we show the word example. Then we put the problem statement on screen in bold orange. Here is the plan. We will reason from the geometric sequence property, take logarithms, and finish by recognizing an arithmetic sequence pattern. Step 1. Because 1 over a, 1 over b, and 1 over c are in geometric progression, the geometric mean property says the middle term squared equals the product of the outer terms. We will display that rule. Then we apply it directly to our numbers. Step 2. We simplify the fractions and cross-multiply. First, reduce both sides. 1 over b squared equals 1 over ac. Now cross-multiply to isolate. We obtain b squared equals ac. Step 3. Take logarithms of both sides. If two positive quantities are equal, their logs are equal. So we write log of b squared equals log of ac. Use the product rule for logarithms. Log of a product is the sum of the logs. That transforms to log b squared equals log a plus log c. Step 4. Move the exponent using the power rule for logs. The power rule says log of x to the n equals n times log x. We get 2 log b equals log a plus log c. This is exactly the condition for an arithmetic sequence. Twice the middle equals the sum of the ends. Therefore, log a, log b, and log c are 3 consecutive terms of an arithmetic sequence. The correct option is 3 consecutive terms of an arithmetic sequence. Let us summarize the full chain in one place. Example, we will prove the inequality. Open parenthesis log base 13 of 19 close parenthesis to the power negative 1 plus open parenthesis log base 28 of 19 close parenthesis to the power negative 1 is greater than 2. Step 1. Start from the left-hand side, exactly as written. Use the negative exponent rule. A to the power negative 1 equals 1 over a. Apply this to each term. Apply the reciprocal change of base identity. 1 divided by log base I of b equals log base b of a. Convert both fractions. Use the product rule for logarithms. Log base b of x plus log base b of y equals log base b of x times y. Multiply 13 times 28 to get 364. So the left-hand side becomes log base 19 of 364. Next, compare this to 2. Write 2 as log base 19 of 19 squared, which is log base 19 of 361, because 364 is larger than 361, and the base 19 is greater than 1, the logarithm is increasing. Therefore, log base 19 of 364 is greater than log base 19 of 19 squared, which equals 2 times log base 19 of 19. That is 2. Finally, we have proved that the original left-hand side is greater than 2. So the inequality holds. Example, if log base 12 of 27 equals a, find log base 3 of 2. We will follow a strict step-by-step path that mirrors the algorithm in the prompt. Step 1. State the given relationship. We start from the equation log base 12 of 27 equals a. Step 2. Apply the reciprocal form of the change of base rule. Swapping base and argument in a logarithm inverts the value. Step 3. Factor the argument 12 as 4 times 3. Step 4. Use the product rule for logarithms to split the product into a sum. Step 5. Rewrite 27 as 3 cubed and 4 as 2 squared. Step 6. Apply the generalized power rule. A power on the argument becomes a multiplier, and a power on the base divides. Step 7. Recognize that log base 3 of 3 equals 1. Step 8. Isolate the term with log base 3 of 2 by subtracting 1/3 from both sides. Step 9. Multiply both sides by 3/2, the reciprocal of 2/3. Step 10. Combine the fractions. 1 over a minus 1/3 becomes 3 minus over 3a. Then multiplying by 3/2 cancels the 3 and leaves the final result. Welcome! In this example, we will solve an exponential equation by using logarithms, exactly following a clean step-by-step algorithm. First, we show the example label. Then, we state the problem in bold orange. Find the value of 3 to the x, given 3 to the x squared equals 2 to the log base 3 of 2. Step 1. Apply logarithm base 3 to both sides. We will use the power rule of logarithms. Taking log base 3 gives log base 3 of 3 to the x squared equals log base 3 of 2 to the log base 3 of 2. Step 2. Use the power rule to bring exponents down. Here is the rule again. We get x squared times log base 3 of 3 equals log base 3 of 2 times log base 3 of 2. Step 3. Substitute log base 3 of 3 equals 1. This identity converts the left side into x squared times 1. So we have x squared times 1 equals the product of two identical terms. Therefore, x squared equals the square of log base 3 of 2. Step 4. Solve the square equation. If a squared equals b squared, then it equals plus or minus b. Hence, x equals plus or minus log base 3 of 2. Step 5. Evaluate 3 to the x for each case. We use the definition of the logarithm, and we also use the negative logarithm property. Case 1. If x equals log base 3 of 2, then 3 to the x equals 2. Case 2. If x equals negative log base 3 of 2, that is log base 3 of 1/2, then 3 to the x equals 1/2. Therefore, the possible values of 3 to the x are 2 and 1/2. Example, if capital A equals, open parenthesis, log base 5 of 3, close parenthesis to the power cosine x, find the maximum value of A. Step 1. Analyze the base. When the base is between 0 and 1, b to the power x is a decreasing function, so it is largest when the exponent is as small as possible. Here, since 3 is less than 5, log base 5 of 3 is less than 1. So to maximize a, we should minimize cosine x. Step 2. Find the minimum of the exponent. Cosine x ranges between -1 and 1. Thus the minimum value is -1. Step 3. Substitute the minimum exponent. The maximum of a equals open parenthesis log base 5 of 3 close parenthesis to the power -1. Step 4. Apply the negative exponent rule. b to the -1 equals 1 over b. Therefore, the maximum of a equals 1 over log base 5 of 3. Step 5. Convert the reciprocal of a logarithm. 1 over log base b of a equals log base I of b. Hence the maximum of a equals log base 3 of 5. Example, we will evaluate capital A exactly following the provided algorithm. First, display the problem clearly. Step 1. Define the exponent b and write the expression for b explicitly. We also show the rule box for this definition. Step 2. Apply the product rule for logarithms. Log m plus log n equals log of m times n. That transforms the numerator. Step 3. Use the power rule and log m equals log m to the n, turning 3 times log 2 into log 2 cubed. Step 4. Simplify 2 cubed to 8, so the inner log becomes log 8. Step 5. Apply the change of base formula to write b as a base 5 logarithm of log 8. Step 6. Translate the logarithm into its exponential form. 5 to the power b equals log 8. Step 7. Following the given algorithm, substitute 5 to the b inside the exponent of 100. Then replace 5 to the b by log 8. Step 8. Use the base swap identity. X to the log base of y equals y to the log base of x with base 10 to rewrite 100 to the log of 8 as 8 to the log of 100. Step 9. Evaluate log base 10 of 100, which equals 2. Step 10. Compute 8 squared to get 64. Celebrate the result. Example. We will find the difference between the roots of the quadratic equation with logarithmic coefficients. Using the given approximations, log 2 is approximately 0.3, and log 3 is approximately 0.4. Step 1. Compute log 30 using the product rule. log 30 equals log 3 plus log 10, which is approximately 0.4 plus 1. That is 1.4. Step 2. Compute log 6. Using the product rule again, log 6 equals log 2 plus log 3, approximately 0.3 plus 0.4 equals 0.7. Step 3. Compute log 5 over 6 using the quotient rule. We write log 5 as log 10 minus log 2. Then log 5 over 6 equals 1 minus 0.3 minus 0.7, which is approximately 0. Step 4. Substitute these values into the original quadratic. Log 30 is 1.4, log 6 is 0.7, and log 5 over 6 is 0. Step 5. Simplify. 2 times 0.7 equals 1.4. So the quadratic becomes 1.4x squared plus 1.4x equals 0. Step 6. Factor out the common term. 1.4x times x plus 1 equals 0. Step 7. Apply the zero product property. Either 1.4x equals 0, giving x equals 0, or x plus 1 equals 0, giving x equals negative 1. Step 8. Compute the difference between the roots. The absolute value of 0 minus negative 1 is 1, so the difference between the roots equals 1. In this lesson, we solve a classic exponential and logarithmic puzzle. We will strictly follow two methods, mirroring the exact sequence and algebra used in the reference solution. First, we present the example and the problem statement in bold orange math. Method 1, using logarithms. We will isolate a and b with logarithms, substitute into the target fraction, simplify carefully, and arrive at the final value. Step 1. Use the definition of a logarithm to solve for from the equation 225 equals 3 to the a. Step 2. Apply change of base to solve for b from the equation 225 equals 5 to the b. Step 3. Substitute the expressions for a and b directly into the fraction ab over a plus b. Step 4. Combine the denominator using a common denominator. Step 5. Cancel the common factor that appears in both the numerator and the denominator. Step 6. Use the product rule of logarithms to combine log 5 plus log 3 into log of 15. Step 7. Recognize that 225 equals 15 squared. Step 8. Apply the power rule of logarithms to bring the exponent 2 down. Step 9. Cancel log 15 to obtain the final value 2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.